Welcome to VALU3S First Training Session, Part 1. This session will cover 5 different verification and validation methods that are going to be addressed during the project. It is now time to start the session. Enjoy.
We are going, me together with two PhD students, Giovanni Gaggero and Alessandro Fausto, who will help me guiding you through this method we are proposing within this project, whose title is Wireless Interface Network Security Assessment. Okay, so first of all, in order to put our proposed method in the scope of the VALU3S project, I just mentioned this sentence from the proposal of VALU3S in this slide, which is the focus of VALU3S is on verification and validation of cyber-physical automated systems. So this is the overall field where our proposed method is going to tackle, and in particular, so related both to cyber and physical security. In more detail, as you can imagine, automated system, currently developed automated system, can be equipped with wireless interfaces, could be Wi-Fi interfaces, radio link, Bluetooth interfaces, different kind of technology, wireless technologies. And behind these interfaces could also be different systems, some of them also vital systems. For example, if you think about the autonomous driving cars, behind this wireless interface could be also the CANBus systems, which is directly linked to vital systems. And if malicious user can get access to these systems, which per se are not so protected from the cybersecurity point of view, as we will see in the next slides, the damage could also be significant. So what we propose, which is the scope of our method, is just to try to improve something which we found in the literature about the exploitation of the vulnerability and the threats that can be, taken in place through wireless interfaces, in order to, on one hand, assess the security of this wireless interface in the use case we are going to consider, but also in general try to improve the testing methods and also the security of these wireless interfaces. And in particular, within this project, we will consider the radio link and the Wi-Fi interfaces, so both from the attack injection point of view, and in some way we will also try to think about if some procedure related to the security assessment could be improvement thanks to the output of our investigation and test. Okay, so I think that now I'm going to leave the floor to Giovanni Gaggero to this technical part, and then Alessandro Fausto, so they can enter in more detail about this method.
Thank you, Fabio. So good morning, everyone. This type of automated system are usually based on CANBus protocol. CANBus is a protocol designed for automotive application in the 90s by the Bosch company, and now it's a ISO standard that defines the data link and the physical layer of the protocol. That was designed to operate in environment with high electromagnetic nodes. So the main purpose, the main aim to the protocol was that to be able to operate in particular environment. Next. This is the frame of the protocol that base the access to the media on current-sense multiple access strategy. So, for example, if two nodes start transmitting simultaneously, the access is managed through the arbitration field. So, for example, one node starts transmitting and has a priority level 4, the other has priority level 5. The first node starts transmitting 1, 1, 1, 1, 0. So is transmitting a 0 and see on the channel a 1 and stop its own transmission. And also we can see from the frame that has a huge CRC field, so the protocol implements a strong error checking method. Next. We can also notice that the protocol doesn't implement any particular security mechanisms. So there's no cryptography, there's no authentication, and it's also quite easy to implement a denial of service. For example, a trigger attack can be just to inject packet with the highest priority level, and so the channel is unavailable. For some reason, it's quite difficult to implement any other mechanisms like intrusion detection system or something like this on the CANBus. So we can see that the protocol basically implements no security mechanism. Next. For the reason, we have to ensure that the main control network is protected from malicious attack. So making a sort of parallel between ISC node that is 62443 for the protection on industrial control system, node that cannot be directly applicable to this type of system, but nevertheless, the norm introduces two concepts that are the zone and the conduit. So a zone is a particular portion of the network that must ensure a security level, and a conduit is a channel that makes two zones communicate and must ensure the same level of security of the two zones. Trying to, as I said, making a parallel to a control network based on CANBus, we have to ensure that all the interfaces that allows to access to the main control network, for example, all the wireless interface must ensure a high security level. Next. And how we can access to, next slide, how we can access to the CANBus network. For example, in Vehicular System, it's quite easy. One of the main methods is accessing the OBD port that is usually located under the steering and is usually used for maintenance or something like this. But also infotainment systems are often connected to the CANBus because, for example, if I want to share on the screen some information about the functioning of the vehicle, for example, velocity, the level of the fuel, and so on, the most simple way is to directly connect the infotainment system to the CANBus network. But infotainment are also connected to other devices, for example, as Bluetooth gateway, Wi-Fi gateway, and many other interfaces. But in this way, we are creating a direct channel between external devices that can be a PC, a smartphone, or something like this, to the CANBus network. So we are usually enlarging the surface of attack. Next. While, for example, in the use case that we are considering, that is the Agri-bot use case, so autonomous vehicle for agriculture application. Also, in this case, we can see that there are many interfaces that could allow to access the CANBus network. One of them is the radio link that is used in this type of application for teleoperation. And often the system has also CAN Wi-Fi gateway that in this case could allow to inject directly paper in the main CANBus network, so directly sending commands to the TCU and all the apparatus that control the movement of the vehicle. And we can also notice that another vulnerability could be represented to the GPS, because GPS is vulnerable. Spoofed can be vulnerable to many types of attacks. And in this case, depending on the strategy that the vehicle used to estimate its own position, This is a huge vulnerability. For example, if the vehicle estimates its own position only with the GPS, it's quite easy to compromise the functionality of the vehicle. So at the moment, I leave the floor to my colleague, who will further explain details of the verification for wireless interfaces.
Hello. We have considered two attack surfaces identified in the Agri-bot schema by the colored areas. The first attack surface is the radio link for teleoperation and is colored in red on the schema. As you can see, an attacker can try to compromise this radio link or device in order to take control of the Agri-bot or inject packet on the CAN1 bus. The second attack surface is the CAN Wi-Fi and is colored in yellow on the schema. This gateway can be attacked by malicious user in trying to broke or bypass the HTTP interface of the gateway and gain control of the CANBus number 2. If the attacker successfully compromises the security of the radio link, can act in place of the original teleoperator, taking the control of the Agri-bot or CAN1 bus. He can send command to the Agri-bot control unit, but cannot directly reach other CAN device because they are connected to other CAN buses. Using software-defined radios tools, an attacker can listen on radio frequency and send radio signals. These tools are available both for Linux or Windows. One of the most known is the tool GNU Radio. The SDR card can work in various frequencies range. By example, the HRF SDR work in the range from few megahertz to 6 gigahertz. The radio frequency used by the teleoperator link stay inside this range. So the radio link protocol is proprietary, but some information can be found searching on the FCC ID database. Sometime we can find radio frequency, and sometime also information about the modulation used and the chip, and also the microchip installed inside the device. The SDR device can be used in different malicious ways. As first attempt, an attacker can monitor the frequency used by the radio link to detect the presence of a teleoperator in the file. Then they can capture and reply all radio link commands. These can be successful only if the device cannot take countermeasure against a reply attack. Can be announced is a random number. Finally, the attacker is able, if he's able to do a reverse engineering of the protocol, it can also build a fake controller. To evaluate the security of the teleoperator radio link and device, we test different attacks on the radio communication channel, starting from a simple jamming to more sophisticated attacks. We plan to evaluate intrusion detection technique based on a statistical approach. By example, we can use radio channel occupancy or radio packet round trip time. The second attack surface taken in account is the CAN Wi-Fi gateway. A malicious user can try to compromise the gateway in order to gain access to the CANBus 2. If this happens, he can send command to more vital device, by example, the human-machine interface or the radio track or the Agri-bot track control unit. But it cannot interact with the device connected on CAN1 or CAN3 bus. To evaluate the security of this gateway, we use OWASP Web Security Testing Guide. This guide provides a lot of different tests to verify a web service use if a web service use all possible defense against most common cyber attack technique. As an example, can be a SQL injection attack on user login form. A malicious and unauthenticated user can exploit a flaw in the user authentication to gain access to protected web page without having the required rights, and can send packet to the CANBus 2 and reach vital device.
My name is Jan. I'm a PhD student at the Sister Research Center, and I'm going to be talking about runtime verification based on firmware specification. And this talk will be basically an introduction to runtime verification. I'm going to be talking about what it is, what it isn't, when to use it, its components, instrumentation and monitor synthesis, what can we verify with it, its relation with the project, and some tools. So let's start with some contextualization, because runtime verification is part of a bigger research field called formal methods. And in the context of values, we're mostly concerned with the verification and validation aspects of our systems. Because of this, I want to contextualize the use of formal methods as another tool for us to use to achieve our goals. With that in mind, I want to start with a quote from Dijkstra that says that program testing can be used to show the presence of bugs, but never to show their absence. And that's when formal methods come into play. The idea is to discover possible flaws by having a holistic perspective of the system instead of sticking with the test cases. On top of that, many safety-critical systems nowadays require a combination of formal methods to certain certifications. It's worth mentioning that I'm not saying that you should stop testing your stuff, but to actually combine the tools that make sense to your problem. I'm just going to leave some success stories for those that are interested later in the presentation. And for those who never heard of it or don't really remember anything about it, formal methods are rigorous mathematical techniques that can be used to systematically specify, develop, and verify software and hardware systems. Formal methods are basically divided in two ways of using it: formal specification and formal verification. First one is formal specification, and as the name suggests, it's a way of specifying something, you name it. So let's say you want to develop a motor controller, and although natural language makes it easy to describe a high-level specification of what it should do, it will be probably full of ambiguities. Formal language, on the other hand, are harder for us to digest, for the human eye to digest, but are much more precise. And that's where formal specification shines, because it helps the developer or the engineer to understand the system behavior, and it makes it easier for them to discover flaws, inconsistencies, ambiguities, and incompletenesses. Nowadays, it's supported by many formally defined languages. And next up is formal verification, that goes a step beyond of what formal specification can do. And instead of only specifying, you can actually perform some check-ins about a model or specification that you come up with. It's divided in two groups. First one is static formal verification, and it's performed during design time, in the sense that you don't need any runtime information to perform your verifications. It aims at exhaustively checking every single possible state of to find the trickiest of the corner cases, which could end up being serious threats in the future. To do so, it also requires a lot of computing resources. A good example of use of formal verifications, static formal verifications, is formally verifying cryptographic protocols, where you can find possible corner cases that could result in security threats later on. The second one is dynamic form verification, and that's that's what I'm going to talk about in this talk, which is basically focusing on runtime verification. And on the contrary of static form verification, it uses runtime information to perform verifications, but it comes at a price of a limited coverage. Runtime verification analyzes small snapshots of the system behavior to issue fast results instead of trying to cover everything at once as static form verification does. So recapping, while on the first you have complex specification of the entire system, on the second you focus on checking smaller parts of the system using runtime data. As I said, in this talk, I'll be talking about runtime verification, but later on, Jose is going to be talking about model checking. So when should you use form verification? It's normally used to complement the cases where static form verification couldn't do what you wanted it to do. So, for example, in the cases where there is it's just too complex for the current machines to compute anything useful of our models, and that's why formal static verification is known by the problem of state explosion. Sometimes you just don't have the data that you need to perform some verifications. Other times it's just too expensive to wait for verifications to be performed, and then you just attack some specific cases using runtime verification. And other times, nowadays tools are too limited to cover all the assumptions that you need for the real system. I also want to clarify some things that are in the literature. So that's my view of what the terms in the literature mean. Because, for example, sometimes people confuse the two terms. Runtime verification is more than just logging information. That's what runtime monitoring means, just logging information. In our case, runtime verification means checking formal properties of your system using a formal specification. Although the two are not really completely dissociated in the literature. Runtime verification is also known as trace analysis and dynamic analysis, for example. It's also important to note that runtime verification does not interfere in the system itself, in the sense that if something goes wrong with the system, the idea is that form verification only identifies it. If you want to take some action on it, this research field is called runtime enforcement. So let's go with an example. Although it's not the most complex example out there, let's say that you want to use runtime verification on a traffic light. To perform runtime verification, we need some elements, which are the formal parts of it. So runtime verification is composed of events, which are things that are observed in the system, some kind of behavior that is observed in the system. It could be a change of state, some timeout, or some trigger that happens. For example, a light turned red, or a pedestrian pressed the stop button. Traces are sequences or sets of events. For example, we saw that the traffic light went red, it went green, and went yellow. And let's say that's one trace that you observed in your system. Then you have a formal specification, which is a mathematical way of saying what the system should be doing. It can be described using state machines, regular expressions, or temporal logic. And the monitors itself is when you combine the formal specification to monitor the data that we saw over here, the events and traces. This picture over here gives a clear idea of what we saw so far. So we saw that a system exhibits events and traces, and the monitor analyzes it. The thing that I was missing is how we connect the two, and that's when instrumentation comes into play. So basically, what instrumentation does is connect systems and monitors. The way that it does depends on what you want your system to do. So for example, if you want your monitoring architecture to be fully developed with software, you need to know that you are going to have some kind of computational overhead. If they are hardware units, you need somehow to probe them, and it's also going to incur in overheads in terms of cost, space, and energy consumption. You can also classify monitors in terms of being inline or outline. Inline monitors are the monitors that are placed inside of the application code, and outline monitors are basically monitors that execute independently of the monitored application. And because of that, you can achieve a better isolation in terms of temporal aspects and logical aspects. You can also increase parallelism by using outline monitors, but you also have to keep in mind that you somehow have to probe the system to obtain the data. Because when you use inline monitors, the monitor is already inside of the code, and it makes it much easier to get information. A classical example of outline monitors is when you have to monitor legacy systems where you cannot change the system itself, but you actually have to use interfaces to be able to get any information out of it. And the last classification is in terms of being offline and online. Since there is not much research nowadays in offline runtime verification, we're just going to focus on online verification, which means that the monitors are running alongside with the system. So there is a spectrum of how tightly coupled the monitors are to the system that ranges from tightly coupled to loosely coupled. And to explain each of these items, I just came up with an example where we have a system that has some component called T, and the system is correctly executing its stuff when a action is only performed after a login was performed beforehand. So for example, in the completely synchronous monitoring, every time there is an event that happens in the system, all tasks are blocked. All tasks are blocked until a monitor can say that something happened or nothing bad happened in the system. So for example, over here, the component T1 performed a login and nothing bad happened. But in the case of T2, it's trying to perform an action before having done any login beforehand. And that means for this monitor that there was a violation of some formal property. The second case is where instead of blocking the whole system, you only block the components of tasks that are related to the thing that went wrong. Third example is when you have checkpoints. The idea is that the system keeps sending events to the monitor, but the monitor only issues a verdict when both all the tasks that are related to that checkpoint and the monitors are synced up in the same checkpoint. With synchronous monitoring, with synchronous detection, the idea is that you only block the tracks, the tasks or components that are performing tasks that can be problematic. So for example, when T1 tries to log in is not a problematic action. But when you try to make an action, it can be a problematic action because it's supposed to have the system, the track or the task actually is supposed to perform a login before performing any action. And the last example will be where the system just sends bunch of events to the monitor. The monitor buffers it, and after some time, it just says if there was a violation or not, based on the trace that it analyzed it. So for monitor synthesis, the idea is that you get your former specification and turns it into monitors in an automated way. You can do it in two ways. The classical way is where you synthesize a block of code, which is the classical way of doing it, the monolithic way. And more modern approach, you can do it distributedly, where, for example, you generate bits of code that are spread in your system, and they can be either orchestrated, where there's like a single unit orchestrating all the other monitors, or each monitor has its own part, which is the choreographed approach to it. I'm just leaving some tools over here for those that are interested, but Copilot is a very well-known stream-based hard-time tool for generating monitors. And I just want to talk about what can we actually verify using runtime monitoring. You can verify actually many things. It's basically up to the tool that you use and why you want to use. For example, event ordering, the correctness of some values, temporal properties. You can also abstract all these things to say that these relate to some safety property or some liveness property. But at the end of the day, you are most likely getting one of these results. It's either true or false, the thing that you analyze. It can also be true, inconclusive, or false, in the sense that the monitor doesn't have enough information to tell you if it's true or not the thing that you want to verify. Or it can also be true, still false, still true, or false, in the sense that at that point where you try to verify something, it was still true, but later it can develop in a false trace, or it can still be true later on. So how do we verify it? The techniques are local quantification, where you put checkpoints in the system, basically saying if you reach that checkpoint, it means that it's good or bad to the system. You can use temporal quantification, where you analyze the temporal ordering of your events. It can either be like relative, saying that one thing has to happen. If one thing happened, there was another thing that happened before it, just like the case that we just saw, where for some action to be performed, there had to be a login beforehand. Or you can actually use absolute values of time. Data quantification is like an extension of the temporal quantification, where on top of having this ordering of the systems, you also analyze how the data changed or didn't change between the occurrence of the two events. And with abstract data specification is where you specify an abstract model of the system, and your runs of the system or your traces and events have to fit in that abstract model. If you want to go to the approaches, I just listed the approaches that are related to the techniques that we just saw. So for example, with assertions, the idea is that you put a statement in your code to check if something is true or not. With pre and post conditions, is that you analyze some properties, some assertions before and after something happened. So it's really common to use pre and post conditions before and after methods to check if whatever happened in that method, if it still complies with the conditions that you set for the pre and post conditions. With the invariant, the idea is that properties must hold at all locations where it is expected to hold. With state machine and process algebra, the idea is that the current run of your program has to be a refinement of another abstract program. With temporal assertions, the idea is to basically reason about, as we said before, the ordering of events. And you also have domain-specific language, where you come up with like complete formal specific language for the thing that you want to verify. finalizing, the idea is to explain a little bit what's the relation of runtime verification and values. In this context, we want to make sure that form verification of monitor generation is correct, in the sense that we make sure that the properties that you want to verify are actually correctly specified. If they don't specify, if you're not trying to verify something that is unverifiable. We also want to kind of make a popularization of RV, and that's one of the things that we've been working on, in the sense that we are creating a DSL, a domain-specific language, to make it more friendly, make runtime verification methods more friendly to the users. We also want to make sure that whenever you enhance your system with runtime verification aspects, that the monitors don't actually have a negative impact on the safety properties of it. So, for example, we want to make sure that whenever you introduce monitors to a real-time systems, that the monitors do not disrupt the scheduling of it, for example. We've been also playing with the idea of using fault injections to check what the behavior of the monitors would be under unexpected situations. And also with the idea of speeding up the testing of properties with formalism to try to find corner cases that with normal testing you probably wouldn't find it. So the conclusion is that runtime verification is a method for formally verifying properties, where we have this timeline of that's the way that you formalize things. So you have your system that it generates events and traces. There was a formal specification of the things that you want to verify. You have the monitor that verifies it for you, and then it gives a verdict saying if the thing that you wanted to know is true or not. It's basically used to complement static formal verification techniques. So it trades the exhaustive search of trying to find every single corner case to a more lightweight way of verifying things, where you just verify limited parts of the system that interest you the most. You can verify many things of it. It's up to you what you want to verify, and also to the available tools. But tool support is actually growing, and I'm just leaving some reference tools for those that are interested later on. I'm just also leaving some references, and time for questions, I guess.
Let's start. I'm Davide Tonella. I'm working in STAM as project engineer. STAM is an engineering firm based in Italy, which is quite active in the safety, security, and automation fields, as well as research and development projects. The topic of this presentation is, of course, risk analysis, which is a skill which is ingrained in STAM for more than 10 years. And of course, today we are most likely to talk about risk analysis applied to automated systems. So, first of all, starting from the basis, what is risk analysis? I've taken the ISO 31000 as a reference because, of course, some of you know that it is one of the most, let's say, important reference standard for what concerns risk management. So basically, the risk analysis is only a part of the risk assessment process, and this phase starts with the risk identification. Then we have the risk analysis, which is, I can say, the most complex one phase. And after that, through that output, we can pass to the risk evaluation. Specifically, the risk analysis is the part which is dedicated to understand the risk and, of course, establish the level of risk. So it is a very complex process which involves lots of factors. And of course, it has the main goal, of course, to at the end establish a risk level for each event which can affect the system. Of course, we are talking about bad events which can cause negative consequences, and of course, it could be the possibility to have high damages, of course, to the system. As said before, risk analysis involves many factors. I've tried to recap here in this slide which are the key factors that we have to consider while we are undertaking the risk analysis. So, first of all, the main factor, of course, is uncertainty, because we are talking about events that have happened, maybe, but we don't know if they will happen again and when. So we have to always cope with uncertainty when we are talking about risk analysis. When we are talking about events, and specifically about malicious events such as attacks and frauds, generally we can speaking about threats. And of course, threats are characterized by the likelihood of occurrence and the consequences, so which are the damages that these threats could cause the system under examination. There are other key factors such as the connectivity, which is very important to date, because of course we will know that we are living in an interconnected world, so we have kind of cascading effect, domino effect, and so on. So it's very important to always deal with connectivity. Existing controls, because you know, we have already some safety measures put in place, and we have, of course, to evaluate the effectiveness of these measures against the threats. Time, because of course the risk can change over the time, can change over the day, over the year, and so on. And finally, the complexity. Of course, complex systems are more difficult to be examined rather than simple systems. So this is something that we should consider every time we need to perform risk analysis. Another important question is why we have to perform risk analysis. So, of course, we can have lots of reasons, but I've tried to indicate these as three main reasons. So we have to protect the values of our assets and, of course, of the system and its component. We have also to safeguard business and service continuity, so basically avoid incidents and attacks could make us continuing the operation, and of course still going ahead with the business without any economic losses. And finally, of course, since the risk is always greater than zero, we are talking about reduced risk, we have to elaborate some emergency response and mitigation plan in order to cope with this risk and, of course, try to mitigate the consequences. There are a lot of risk analysis methodologies existing nowadays. So also here I tried to define some categories in order to divide the methodologies in a smart way. So of course it could be dependent on the type of output. So we can have qualitative risk analysis, which can provide us just a pictures, maybe through words, or we can have quantitative results expressed as number. We can have deterministic results, or maybe stochastic. Of course, as I said before, uncertainty has to be taken into account, but anyway, we can also have some deterministic outputs anyway. We can use a scenario-based approach, so we can start identifying the scenario and then understand which is the risk level of each scenario. Or alternatively, we can start from threats. We can then generate scenario and in the end calculate the risk of this scenario. And finally, we can have some risk analysis, which are very tailored to some domain or some use case, or otherwise we can have some general purpose risk analysis which can be applied to several domains and use cases. Going deeper in detail about the methodology proposed by STAM, I firstly can say that this methodology has been developed in several research and development projects across the last decade. So this is, as I said before, something very ingrained in our company. And basically, our risk analysis methodology is a quantitative, deterministic, threat-based, and cross-territorial methodology. So these are the features that we have selected because I think that this can bring an added value to our methodology. These are the main steps of the methodology. So of course we need some inputs. As usual, we use basically a model of the system. Some historical data related to the threats that we are considering, some economic figures, the safety and the security measures existing, as well as some sister properties that, of course, can change according to the typology of the system. The first step is, of course, the scenarios generation. So, as I said before, we start from threats. We consider several factors, and in the end, we generate a large set of scenarios. After that, we have to simulate these scenarios, so understand how these scenarios could evolve, also considering the effectiveness of the different safety and security measures that have been implemented in the considered system. After that, for each scenario simulated, we should compute the likelihood and the impact of this scenario. And in the end, as outputs, we can have a sort of risk level that we usually express as euros per year, or other outputs explaining the consequences. That could be, for example, the number of casualties, the number of injuries, the number of physical damages, the economic losses that could be generated by the consequences, such as also, for example, the revenues losses due to business interruption. Just to be very clear, this is a methodology that today we have applied mostly to critical infrastructure. So only recent year we are trying to tune these methodologies to automate the system. So maybe sometimes you can find some reference to, let's say, to features or characteristics about critical infrastructure. This is basically the scenario 3 that we usually model into the algorithms of this risk analysis methodology. So, of course, as a start, we consider the type of threat. So it could be an attack, an incident, or a failure of the system. After that, we should consider the entry point. So basically, from where the threat can enter into the system. So you know that for each threat, we can have several different entry points. We should consider also the target, so which is the system of the component of the system to whom the threat occurs. The magnitude of the threat, which is kind of measure of intensity of the threat, we basically divide this entity in different levels, such as low, medium, and high. We have also to consider the time slot, so that when the threat occurs, because as I said before, time is a key factor and the risk can change along the day or maybe along the year. And finally, we have the outcome of the scenario. So basically how the threat evolves. So as I said before, we should simulate the scenario and understand the effectiveness of safety security measure, and of course, at the end, how the scenario evolves. Here is just to give you an example of the complexity of these scenarios 3, because basically considering these numbers, which are not so high, at the end, we basically generate a very huge number of scenarios. So, as you can understand, it is very difficult to analyze manually this such large set of scenarios. So, of course, starting from this output, we decided that this methodology should be implemented in some way through an application. So our idea basically was to create sort of microservice to perform risk analysis of different systems. So basically we called this microservice RAMSES, which stands for Risk Analysis Microservice Solution. So basically RAMSES is a sort of web service which is composed by, of course, a database containing lots of information about threats, about system properties, and so on. And then we have, of course, a computation engine which has been developed in Python, which basically contains all the risk analysis algorithms that we use, of course, to carry out the risk analysis from the beginning to the generation of the results. Using these microservices, we have basically built lot of web application for risk assessment, which basically exploit this microservice. So web application can send inputs in JSON format to this microservice. Of course, here we can use, for example, a broker such as Kafka or other interfaces such as REST API. And then, in turn, the microservice provides the web application with outputs in JSON format. Again, going briefly on the input to the microservice. Yeah, this is just an example of possible input, which is most referred, as I said before, to critical infrastructure. So basically, the most advanced input that we could provide now through our application is a graph database representing the system under examination. Of course, this database contains all the information of the components of the system and also of the relationships between the components of the system. So here we have an example referred to critical infrastructure. So we can say some areas, some assets, some security measures, and of course a threat that could be perpetrated against the assets of this critical infrastructure. So this is just an example of which are the data that could be ingested by our microservice. And then, of course, the microservice provides the web application some with some useful outputs. The most important is the risk register. The risk register is kind of document containing all the risk scenarios generated and analyzed by the computation engine. And of course, for each scenario, the microservice provide a lot of information, such as the main variables, defining the scenario, the likelihood, the impact, the different kind of impacts, and of course, the risk level of this scenario. Starting from this register, we could then elaborate and aggregate the output to obtain different indicators that could be, for example, sort of global risk level of the system, global vulnerability level, risk profile during the day or during the year, according to the time slot that we are modeling, and of course, sort of detailed risk and vulnerability levels for each component of the system. Now, just to give you a very rough idea, I would like to show you a short demo about the last web-based application that we've developed for another project, which is called InfraStress, which is an Horizon 2020 process concerning with the protection of critical infrastructures in the industrial domain. Can you confirm that you can see the web application now?
Yes.
Okay, perfect. So just to give you an idea, here in this application, we can model different critical infrastructures. And for each critical infrastructure, we can model different configuration. Here, for example, I've created one configuration for, let's say, a kind of minimum protection standard, and another one for what could be sort of maximum protection standards. Basically, first, the user is requested to edit its own infrastructure. So basically, it can enter some useful data for the risk analysis, such as the country in which is located the critical infrastructure, the number of employees, the value statistical life, which is kind of measure of the economic losses in case of fatalities and injuries. Then again, the user can enter the security measures which are implemented into the facility by simply drag the item from the list and drop it in this blue box. Of course, again, the user can delete this item. The same can be done with some with the areas of the critical infrastructure. So just to give you an idea, we can try to edit an already existing area that I've modeled for just for this demo. So I take this area, which is a tank farm. So the user is requested to enter the size of this area, the economic value per square meter, the presence of hazardous substances, and then also the number of people within this area during the different time slot of the day, which can be basically modified with this slide. Then again, which are the security measures that are effective on this area. And finally, which are the assets that are placed within this area. So here, for example, we have kind of electrovalve, several tanks, and of course we have also some security measures which insist on the assets. So we can also activate some of these security measures. So after that, we can basically save the configuration, and basically the modeling of the system is completed. After that, we should basically click on the button Run to have the results of the risk analysis. Of course, we have to wait for a few seconds, and while in the moment the web application is contacting the microservice, and the microservice is running the risk analysis algorithms. And after that, we can basically have a dashboard with all the indicators useful to the user for understanding the system. So, for example, we can have the total annual risk level, which is split according to the attack which can be perpetrated to the system, but also split with the risk source. So, for example, fatalities, injuries, physical damage to the infrastructure. We can have also some indicators about vulnerability of the system according to the different attacks, or the daily risk profile in this case. So according to the time slot of the day, we can see the risk levels split in different attacks. And we can have also the loss exceedance curve, which is kind of indicator which explain the likelihood of having a loss greater or equal to the expected loss that we have in the X. Then we have another dashboard, which basically shows all the components of the system that we have modeled before, and for each component we have the risk level as well as the vulnerability expressed. So this is kind of spatial distribution of the risk. We have also kind of chromatic scale in order to allow the user to understand which is the most risky components of a class. And finally, as I said before, we can also see the risk register exported as a format, as an Excel format, which is of course is the most completed information. It contains all the scenarios that have been created for this data. So, for
now
example,
I just want to take some pictures
case,
for the demo.
we have generated 13,230 scenarios. So this is a very sorry,
there's a
noise.
kind of a training
Listen
session
to your
for
microphone.
the project. They just talk about some methods. Huh?
Sorry, there is some background noise. Please let Davide finish his presentation.
Yes, I was saying that this is the risk register containing all the risk scenarios that have been generated, simulated, and analyzed by the microservice. So, as I said before, this is a very huge number because here we have around 13,250 scenarios. For each scenario, as I said before, we can see the main coordinates of the scenarios as well as the outputs generated by the microservice using risk analysis algorithms, such as the likelihood, the different impacts, number of fatalities, number of injured, physical damage percentage, and the economic losses which are generated by these consequences, and of course, in the end, the risk level which is associated to all the scenarios. So, coming back to the presentation, just for the conclusion, these are the improvements that we would like to implement in values. Of course, we have just started the work in this task, so the improvements are still work in progress. So the first goal is, of course, to continue in the refinement of the methodology, to adapt it and make, say, this shift from critical infrastructure to automated system. Another important goal that we want to achieve is reach a detailed modeling of the cascading effect, which is, of course, a very important factor which shouldn't be neglected because, of course, as I said before, we are living in internet connected world. We would like also to try to add to the microservice and to the methodology the capability to cope with lack of historical data, because of course for some threats such as cyber attack, we basically miss some historical data, or we have few of them. So the idea is to try to use artificial intelligence to in some way generate simulated data, or anyway have kind of forecasting about these threats without having any historical data set. And finally, we would like also to implement sort of real-time risk analysis using, for example, the feedbacks coming from different sensors of the system in order to carry out a sort of rapid impact assessment that, of course, could provide the user with some important information and at a glance in order to properly react and also mitigate the consequences of the threat which is occurring. And that's all from my side. I hope I made it clear. And of course, if you have questions, please feel free to ask.
So I'm Joseph from ISEP, and this will be an introduction to model checking. So we'll not talk about our use case, our method. We're going to mainly try to make sure that the concept of model checking, which is used by many partners here, is clear for those partners who are not so familiarized with the concept of formal methods or model checking. So first of all, before I start, I want to make very clear that model checking consists on checking some kind of requirements over some kind of model, and this is formal methods. So by formal methods, I mean that both the requirements and the model are specified using some kind of mathematical data structure, which is very well known and understood, where we can apply transformations, analysis, and so forth. So in this training section in particular, what you're going to see first is what are exactly these models. So typically these are some kind of transition systems that also are built using some other notion of composition. Then we'll take a better look of what requirements are in this context. So these are typically logical expressions using some kind of logics, and there are many kind of logics we can use. And I'm going to illustrate these concepts of model checking using two model checkers I'm familiarized with, but there are many others. So I'm going to show quickly how MCL2 works and how UPAL can be used as well. So the main idea is that you know what it means to grab an existing system and represent the model, and then represent the requirements using some logic. So many of you are already familiarized with you, so this will not bring anything new. But if you've seen the name model checking, somehow this might help you understanding exactly what it means to perform model checking to a system. So this is very important. The first thing I want to say that all formal models are wrong. And by wrong here, I mean that when you want to model something, the first thing you do is take out all the details that you think are not relevant until you're able to get a more concise model that abstracts many of the things that are present. So you don't want to include your programs and all the details that are present in your actual system, software or mix of hardware and software, but you want to have only the details that are important for your system. So all are wrong, but some of them are useful. So that's the main goal of model checking, or the first process of building up a model, is being able to make sure that when you abstract, you are able to abstract the exact things that allow you to end up with a very small, compact model where you can control the state explosion and how much you can explore your system, but make sure that the analysis that you make over this model somehow reflect your actual system. So in model checking, there's this huge phase in the beginning where you make sure that the model you have is actually useful, and that's the starting point. So I'm not going to use any complex example. In this presentation, I'm going to use a very popular example in our community, which is modeling a coffee machine. So a coffee machine, in this case, you have a coffee that can be brewed, and you have some interface where you can insert coins, press the buttons, and there's internally some state machine behind it. So I guess this is very popular in the more fundamental community because that's the kind of thing we constantly need in order to produce results and papers. So in this context, we usually write this to capture the model checking process. So we describe some kind of model, this funny M. We describe some kind of state, and we ask ourselves or ask the tools, does this model in this state particularly satisfies or models entails the requirements specified by this formula? So this is the mathematical notation, and basically means that we grab some requirement, a more complex system, typically a state machine, and then we try to check using some kind of brute force or something smarter if we can say yes or no to this property. So that's the key of model checking. So in this example, one possible abstraction or simplification of the internals could be this. So we can build a three-state machine where we can start by this S1 and at some point insert some coin. At that point, we can either give up or make a selection. And inside each state, so finally in S3, we can start brewing the coffee. And at some point, we can get some change back if it exists. So we can also have this notion of prepositions. These propositions, which mean coin, selection, brew, they are basically logical, they are Boolean variables or Boolean expressions. So something we can check or not check in each of the states. So right now, they are some kind of variables, but can be something more complex than that. So in here, we can see that typically this model inside, they consist of a set of states, a set of actions that connect the states, and a set of propositions of something we can check in each of the states. And getting the right model is very often something non-trivial that requires a lot of iterations, refinements, because this can get very big very quickly, and it's not easy to be able to filter out the essentials with respect to the properties that we want to prove. So that would be our running example for the rest of this presentation. But for example, in the context of the use case with Bombardier, we actually trying to get a similar model to this, but more complex one, to understand if a system running multiple redundant processes that need to be synchronized somehow, if you can guarantee that they always keep in sync with when can this go wrong, using also some time restrictions. So this model can get very complex very easily. So this is the model. I'm trying to change slides. Yeah. And now with respect to the requirements are these properties right here. So we can write something like, does this model M on top in state S2, does this formula called coin holds, which means does the preposition coin holds when in state S2? So here the answer will be yes, because this coin has this check mark next to it. Another possible model checking property could be, does this model in state S1, if we make if any possible way of making this action called make selection, will the proposition selection hold? So these are already including actions in the middle of our formula. So these formulas can actually contain more complex things, and the expressivity of this formula capture what kind of requirements we can specify when you look at properties we want to reason about. So right now I talked a lot about actions and states, and this is a trend you can see quite often when looking at approaches to model check. So I'm going to now take a better look at these two approaches. So there's an approach that quite often looks at the actions. So what possible sequence of actions are possible or not possible, desired or forbidden in our system. And very often these systems use the kind of process algebra to generate these transition systems. And indeed, in this case, we don't really care about the propositions themselves. What we care is about the actions, the traces, the path we take. So we want to make sure certain kinds of sequence are possible or not possible. And this is very useful, especially when you're modeling interacting systems and you want to reason about the interaction between them. So another approach is this focus on states, where you see these labels no longer have any information, and what you care is about reasoning about the state. So you want to care which states are reachable, which may never be reached, and something in the middle. So quite often use some kind of language or diagram or automata to be able to generate what exactly mean by our model, our transition systems. And here quite often use these propositions somehow enriched with some kind of modalities. So special keywords or expressions that describe if it's for all possible paths, if somewhere in the future, in the next step, or these kind of constructions. So before I go into this, I just want to bring two small notes. So the first note is that the logic used and the notion used for your model, they are tightly related. They are very interconnected. So, for example, when you say these are the kind of logics you can express, these will induce automatically some notion of equivalence here. So the class of models that obey the same logical propositions. And this often corresponds to the notion of bisimulation, for example. And you can have other notions of equivalence, like they can perform the same paths, which are similar but different things. So it becomes very important when you model your system and modeling your properties, you understand very clearly what does it mean to have two equivalent systems, also with respect to the properties. So this is often studied multiple notions of equivalence if you want to simplify this and how this impacts the properties you have here. So that's more on the more formal analysis of the system. And similarly, you can also analyze the notion of inclusion. So inclusion is very useful if you want to say, I have this system, a set of properties. Can I replace this system with something smaller or something more refined? So this is typically something that simulates or has the same traces. So these are the things you can investigate once you have the model and also a set of properties you care about. And the final goal is to be able to drive a model that captures exactly what you need to know in order to show the requirements. So once you have a notion of the kind of requirements you need, then the goal of modeling becomes filtering out and making sure this becomes very, very to the point without introducing unnecessary details. And this is by far not an easy task. So my second note is on the choice of the model and the logic. So there are many, many logics, and I'm not going to go through these logics, but quite often this is the starting point. When you look at the requirements, you understand, do I need to reason about the actual time that things take between different actions? Or do I need to have actually more refined notion of time, and you have this notion of differential dynamic logic? So if you need to specify the evolution of the state using differential equations, which is very common when you interact with physical systems like accelerations of a vehicle or something else. You also sometimes need to know and reason about beliefs. If you have multiple parties, multiple agents, you want to know who knows exactly what and who trusts who, you start talking about the notion of beliefs with what so-called epistemic logics. And similarly, you have deontic logics to reason about mandatory or actions you may be able to do at each state. Logics that talk about values, so you don't really say just a value which has yes or no, but you can actually assign a weight both to your system and to the logics you want to express. Probabilistics is a subcase of this fuzzy logics where I can talk about the probabilities of something happening. And there are many tools for this. So these are the kind of tools I've been encountered. So MCL2 and Newpal will see now a small tool demo. So Spin is very common for probabilistic systems. This new SMV or extensions is something that it's also being built among our partners. So Stefano from Bruno Kessler Foundation, I think they are the ones actually involved in the creation of this. Microsoft tries to push this TLA Plus, which is already quite old but still being used in practice. Many tools over Petri nets. So there are lots of tools that help you building models and verifying logical properties with different variations of logics and even within inside of each of these model checkers. So if you care about any of these, you can contact either us or other members that will actually be able to help you guiding on how to build models and logics for your own systems. So let's go now with a small tool demo. So I have two very short tool demos. The first one will be to show this MCL2, which is developed in Eindhoven in the Netherlands. And this is something completely free. So there are no commercial connections, and they actually being used quite actively in several industries. So this is well known because it works quite well with large systems, and they focus on actions. So if you look at our system, typically they don't look at these propositions we have here. What the system that is built is mainly focused on verifying what kind of actions can be executed with possible traces. So this will be our way of modeling in our system. So you write in something that's called some process algebra, and you say that in the beginning, we can perform a coin action followed by a choice. So this plus captures the choice between either selecting and starting to brew or aborting and returning to the start state. And once we are brewing, which is this S3 state, we can perform brewing and return to this brew state, or we can choose to give some change and come back to the start state. So this is the way we actually write the system. And you can go further than this. We can actually build composition of systems that have actions that are force synchronized with other actions. So I'm going to open now M3L2. So let's see if I find the mouse here. So the simple example here basically means that you have this IDE. You write here what kind of actions you have, what are your processes, and you say, I'm starting with process start. And the kind of things you can do often is you can ask to show the state space. So in this case, it's a very small state space. This is exactly the system we had behind. We have only 3 states, but the number of states grows very quickly when you start introducing more details to your system. So I'm going to close this. Other things we can do is also ask to simulate. So once you simulate, you're basically selecting actions. I just did the first action called coin, and now I have the 2 options to perform. So I keep performing actions as I click, and you have the trace, the path we took. So this is useful once you have a very big system and once you start having some intuition of what's happening. So simulation, seeing the state space, and finally we were able to verify things, but this I'll show in the next slide. So once you have your system model properly, the next thing you want to do is to verify. And that's where the logic comes at hand. So we specify different logical properties. I'm going to show an example of this first one. And this language is very, very precise and sometimes not very clear how to go from the natural language specification into something that actually captures the logical property. So in this example, you have this property saying, always, no matter what, I want to make sure that eventually I can get my coffee. So brewing is possible. So this is how I specify here. I have these square brackets and saying, no matter which actions I do, so this true captures any action, the star means any sequence of action. So after any possible set of actions, so after doing a coin, a select, and the board, I did 5 different actions, then it must exist this pattern. So there must exist a sequence of 0 or more actions where I can perform brewing. So no matter how far I reach, I can press some buttons into some coins and make sure I can get my coins. I can get my coffee. So there are other variations, some more complex and less complex. Brewing is always possible. This feels very similar, but this is the same as the top one, but basically saying that no matter how many steps I do, then it exists the possibility of brewing. So by dropping this true star. So this will be false, which basically means I cannot always get a coffee. If I don't put a coin, I'll not have a coffee. So, and there are a lot of subtleties that you can do, and if you change this a bit, you'll change the interpretation, and it's something that is also part of the process of verification, is get these logical properties right. So in our running example, I lost the mouse, here it is. I have here a small property saying I can brew. So it means it's possible to execute, it's possible to execute a sequence of steps where brewing is possible. So if I save and ask to model check will tell me yes or no. And in this case, I can also ask to show a witness, an example of how come I can actually brew a coffee. In this case, the example is in terms of a subset of that graph, saying here's the possible path to be able to perform the brewing action. So model checking, in a nutshell, means specifying your model, specifying your property, and hopefully get a yes or no. And in more advanced cases, you can actually get either a witness or a counterexample where your property failed, but this is not always possible. And there are certain properties where you can try to guide or give scenarios that try to explain why this holds or not holds, but not always you can present this. So this is MCL2, at least a very short view of it. And now I'm going to jump into the other tool, UPAL, which also exists for many years. So this was developed by the Uppsala and the Aalborg universities in Sweden. So this is not free anymore in the sense that commercial projects actually need special licenses, but for academic purposes, we can use very easily. So in this system, what UPAL does is ignores all these actions. So we can actually introduce some notion of action, but the action is only used for synchronizing between parallel systems, and it's not used for this model checking part. So in this case, they focus mainly on the states and on this proposition that you can have here. So this is how we define. So actually draw it using some graphical tool, and you'll say that in state S1 we can go to S2 and you update the variable called coin and make it true. Initially, we set all of them to false, and as we traverse this system, we keep changing these variables. And these variables are booleans, but can also make them integers or something more complex. But typically, you want to make sure this is bounded to make sure that the state space is not growing too much. So in this case, they also have the possibility of modeling some time properties, which cannot do before. So to give you a very small flavor, we assume we have this special variable t. So t looks like an integer or number, but it's actually a stopwatch. So it basically measures the time it passes. When going here, we say that this stopwatch is set to 0, and then stopwatch keeps evolving. We have also this invariant saying that we cannot remain here if the stopwatch increases more than 8, and we have an action that has some guard saying we can only perform this action that corresponds to the brewing action if time is actually greater than 5. So you can specify some extra temporal properties, and these are very useful in some systems, and it's the kind of thing you're also exploiting in our use case. So let me jump into UPAL. So UPAL is here. And let me run our example. So this is the example we saw there. UPAL does not allow you to explore anymore the state space more precisely because there's some notion of evolution of time that's not explicit here because it's already very graphical. What we can do is to ask to simulate, for example. When we simulate, we can see that coffee has certain variables here, and there are some time constraints. And here you can choose the action we can do. So this coffee is selected, which means the coffee machine can do this action, which is in red. I'll just double click here. And then we see that now we are in state S2. So we're basically trying to go through the system. The constraints keep changing. Now we have two options. As I click on them, the red arrow changes and saying which option I can actually choose. And here we have the trace, so the path we took to get there. So this is one way of going through the system, building some state machine as we go. And this is especially useful if you have communication between multiple automata. So instead of one, you can have 2, 3, 4, and again, having some certain arrows being force synchronized with other arrows that are in parallel. So this is the composition aspect, which I just don't have time to go into detail here. And we have this verification part. So the verification part is something I want to go after going to the next slide. So before we had the system with one logic, now we have a different logic to reason about this system. So the same system, but now we can ask something very, very similar to what before, which means, can I always get eventually a coffee? So here, this property here actually means no matter what kind of choice I make, is it eventually possible to get a coffee? This seems very similar, but it's not the same as the previous expression, because not for all choices I can always get a coffee, in the sense that if I choose to insert a coin and then give up, and try a coin and give up, so basically I have a behavior where I choose always something, but not something that leads me to get a coffee. So it's not possible for all possible choices to have eventually in the future the brewing of a coffee. So to have this brew, which only holds in S3. So it's possible to specify more properties. And on the next slide, I'm also going to explain better what this syntax means. But sometimes like this property where it says, no matter which choices, for all possible choices I can make in my system, at every single step in the future, for every possible state I can go to, then previous S1 implies S2. So this previous S1 is a new variable. So sometimes you actually need to go back to your system and extend it with some variables just for the model checking purposes. So this means if the previous state is S1, so you have a variable that says the previous state is S1, then S2 must hold. And S2 is already a special variable to say we are in S2. So this way we can also model something like if I choose a coin, then I'll be in this state. And you can also reason about the values of these stopwatches. Is it always possible that if I'm brewing, if brewing is true, can I guarantee the time is different from 10? So I never spend more than 10 time units waiting for my coffee. So you can also exploit these time properties, and that's how time is expressed in the properties and in the system. Finally, there's also this kind of implication, but this is different from this implies here. So this is the temporal implication. So this basically saying, if I introduce a coin, am I guaranteed that I'll have a coffee, or that will be coffee somehow in the future? And this does not hold, because in our model, we say it's possible for the person to change his mind and abort the system. So this gives you a view of how to write these properties. It's an extremely simple system. So this can be considered actually to be not a good model, because it allows some kind of infinite behavior. So we can do actions without time being passed. So there are actually restrictions that you need to know when modeling time systems, but this will not be the goal of this presentation. So just to give you now back to our UPAL, once I have the mouse sometimes disappears. Here it is. So we can go to this tab for the verification. And you can see, you can write these kind of properties we have here. The first coffee asks, does it exist a set of choices such that somewhere in the future I'll be able to brew the coffee? So can I actually have a coffee if I want to? And if I check it, it becomes green saying, yes, everything's okay. And we can do the same kind of thing for the other properties. In this case, the red means no, it's not guaranteed that for all possible choices you make, you will get a coffee in the future, because you might do choices that do not get you a coffee. And you can also ask to get a trace. To get a trace, we'll say, yeah, we'll create a simulation for you. And once you go to the simulation, it will show you a path of choices saying that's how I was able to traverse your system to actually get this system. So very similar to the witness we saw before. So this is almost my final slide. I hope I'm not taking too long. So this is just to say that you can actually group these kind of properties in Opal as safety properties. And by safety properties are the ones that says, I can guarantee that some property fee will actually hold always in the future, either for any possible choice I may make, or if I'm smart enough, I can make sure fee always holds. So these are called the safety properties, and these properties are typically invariants, saying something bad will not happen. That's why it's called safety. We also have quite often these reachability properties, which are very useful in some systems, and very often the main thing that model checkers try to be good at, which is to show that can I actually get coffee at some point if I'm smart enough, and am I guaranteed that at some point I'll be able to get coffee? And this is a typical reachability question. Other liveness questions like this, or a refinement on that one, means if no matter which choice I make, can I guarantee that something will happen? So this is guaranteeing that coffee is possible to be achieved. And a refinement which is useful, which means, can I guarantee that if I put a coin or if something happens, am I guaranteed to get the coffee? So these are the temporal property that is actually a shortcut for something a bit more complex. And Opal also restricts the kind of combinations we can make of this, just to make sure it's actually decidable and you can get it in feasible time. So this was my short overview over model checking. So what are requirements? What is the model? There are many, many tools. Getting the model right with respect to requirements you want is difficult. I illustrated with two different model checkers that have different mentalities. I did not focus so much in composition, but this is something very important, how to build big systems by composing different processes here or different automata here. And we can have lots of flavors for these logics. So I hope I helped at least some of you understanding what model checking means. If you have any question, please let me know.
Hello, everyone. Thank you so much for having me. My name is Mateen Malik, and I'm an industrial PhD student at Rice. So today I will present our method, that is simulation-based fault and attack injection at system level. So these are roughly the points that I will talk about today. So the first one is basically simulation-based fault and attack injection on system level. So I'm planning to present on a high level the importance and the validity of simulation-based verification and validation on a system level, and also at the same time introduce the method that we will be working on, or we are working on already. After that, I will be presenting sumo-based fault and attack injection, and then the idea is the same, that I will introduce the method and also provide some demo. One thing to be noted here, that this is mostly focusing on the vehicle part of fault and attack injection. Then I will present the sumo veins-based fault and attack injection that focuses on the communication level fault and attack injection. And the idea is to introduce the method and also provide some demo of it. And finally, try to have some minutes for the discussion. So the time I will spend is approximately 15 minutes for the first part, 10 minutes for the second part, and 5 minutes for the last part, and then 5 minutes for the discussion.
Thanks.
Great. So as you already have maybe have realized, that I have used some terms here, which can be the name of the tools or the method itself. So I think it's a good idea to to present the definitions of those terms that I've used here, because I will be using these terms later in my presentation. Sumo is basically simulation of urban mobility, and it's a free and open source traffic simulator. It was available since 2001, and it's a microscopic traffic simulator where each individual has its own attribute. Those include the road vehicles and public transport and pedestrians. VANS is basically also a free and open source framework for running vehicular network simulations. And VANS is based on the two simulators. One is OMNet++, that's an event-based network simulator, and Sumo that I have already talked about. So in VANS, it is possible to model the inter-vehicle communication simulations. So in various industries, the areas where lots of investments has been made and will define how our future looks like. Those are automation, connectivity, and electrification, etc. This brings many advantages to the society, of course, but at the same time increases the risk to the automated and interconnected safety-critical systems. The risks are basically the development and operational faults, and also the security threats, such as the intentional attacks to compromise the system. So the importance of verification and validation of these areas have also increased at the same time. Our method is applicable within automotive domain here, and will facilitate the verification and validation by injecting faults and attacks. As our use case is within automotive domain, so I will focus on it in the coming slides. Okay. So here is the it's the verification and validation stages, or also called integration steps, that mostly are in use or within the automotive industry to verify and validate a system. In this case, it's a vehicle, for instance. So the first starts with the simulations. In simulations, it could be software in the loop simulations or model in the loop simulations. And then one main property of this stage, that there is no hardware involved at this stage, and the software is developed using simulations, as well as it's verified and validated using simulations as well. Then in the next stage, that's the bench. In the bench, it is a mix of hardware and the software. The focus is basically on a particular ECU and the functions residing in the ECU. So all the simulation environment built around it, that is specifically for the base software verification and validation of a certain ECU. So this is the basic hardware in the loop system that we can say. In the next stage, the hardware in the loop comes in. This is a little bit more complicated. It has multi-domain systems. For instance, in the automotive, it could be the steering system, braking system, active safety system, etc. So it's possible to integrate those in this hardware in the loop stage. So here the dynamic functional testing can be done, which means that we can run the scenarios and that can actuate or activate certain functionality, and we see if the functionality is according to the requirements or not. Then comes the test track. So in the test track, it's basically a complete system. So it's a whole vehicle with all the integrated ECUs and the vehicular dynamics, etc. And then the purpose is to test test some subsystem or a system or some function in a controlled environment. Same goes to the field testing, that is in the public road, but the environment is controlled and the system is verified and validated in the field test. Finally, it comes public road testing. So mostly the certifications are done. Actually, they can be done on test tracks as well, but they can also be done on a public roads, especially in the case of autonomous drive systems. So here the purpose is that to run a system without any faults and errors in the system for some amount of time, to make sure that the product is safe and secure before releasing it to the end customer. One thing that is to be noted here is that every stage is also starts from the simple simulations, for instance, here to the complex level. So you see these white lines here, and that represents that the verification and validation of each stage, it never stops when the next stage verification validation in the next stage starts. So in case of simulation, it can, as I said before, that it can be used for a simple verification of very simple functionality in a very early development stages, or it can also be used later in the later development stages when we are also doing the field testing. So it's kind of a feedback loop here, and the complexity increases in the horizontal domain as well. So this was more or less the overall view of the verification and validation stages needed for a vehicle. But we will be focusing on this stage, the simulation stage, where the system is simulated, no hardware is involved. But as I said before, as we move up into the ladder, so the more hardware is added to the system, and eventually it's a complete vehicle. Moving to the next slide, so to highlight the importance and validity of verification and validation in the simulation environment, I thought it's a good idea to present this three-pillar approach that is proposed by OICA. OICA is the voice speaking on automotive issues in the World Forum. And OICA members represent the global auto industry, basically, that drives economic progress. Then GRVA. So GRVA is the UNECE Working Party on Automated, Autonomous, and Connected Vehicles. So OICA has proposed a new innovative certification schemes because, as I said before, the complexity for the automated systems, in this case autonomous drive system, has increased a lot, and a new type of certification scheme is needed. So here the proposal is about the three-pillar approach. This is needed for demonstrating the level of safety and reliability, which allows for safety market introduction of automated and autonomous vehicles, both AD and ADAS vehicles. So AD is the autonomous drive system, level 4 and 5 SAE levels, and ADAS is the assisted driving active safety functions, basically. So the whole idea behind this is to perform bulk of testing in the simulation environment, which can produce comparable results with the actual testing, such as when the hardware is involved, and then move up to perform the physical domain, that is basically, in this case, the real world and the test tracks. So the purpose of the GRVA, so these are the focus for us, that safety and security of automated driving system and connected vehicles. We want to devise some method which can ensure the safety and security of interconnected systems. Also, the validation methods for autonomous driving, VMAD, cybersecurity aspects, and within ADAS, this is interesting: remote control maneuvering and remote control parking, and automatically commanded steering systems, etc. So there is some text here as well, which tells that in order to reduce as we go up, basically. Okay, so OICA has also presented this table that actually some of the requirements are mapped to the three-pillar approach of verification and validation that I have presented before. So no need to look into all 13 principles, but the most important ones for us are basically security and the safety of the system and function. So as we can see that the mapping here that so the proposal kind of agrees that if we want to test the security part of the system, that we can actually do in the simulation environment, and same as the functionality, the failure strategy, redundancy and redundancy concept, etc., into the simulation. And later on, here it's not crossed here, but maybe we could verify what we have tested here to the upper parts of the 3 pillars. Okay, so talking about the virtual testing or simulation, there are 3 main components that we need to consider. So the first one is the functionality. Functionality is basically what we want to test. Is it a system or a subsystem or a function? Within function, it could be an active safety function, AD and ADAS feature that we want to test, or any other thing, for some traffic sign information function, or it could be anything here. But we need to know what we want to test. Then we need to have a vehicle, and then the parameters of the vehicle, like tires, chassis, and vehicle dynamics, etc., because the function is connected to the vehicle, and the vehicle is basically driven in the scenario. So scenario is also very important. So if we want to actuate some specific function in order to test the safety and security aspects of those functions, we really need to think about what type of scenario we need and what type of scenario can actually actuate or triggers that function, and what scenario is dangerous or not dangerous for that specific function if something wrong happens in that function. So scenario has a big role to play when we want to verify and validate certain functionality. Okay, so as I said, like our method will be used for fault and attack injection on system level simulations where the system components are simulated. So we are here in the simulation part, and we are using Sumo to create the use cases for verifying a certain function. So the result actually it verify some capability of the vehicle, and we can categorize those capabilities into either it's a nominal capability or an extreme behavior of the vehicle in terms of faults and attacks. Okay, so I also wanted to give overall view of what test standards are relevant for us or are also relevant for autonomous drive verification and validation in terms of safety and cybersecurity. So ISO 26262, it mainly handles the systematic end-to-end failures, random failures, and also talks about or recommends the safety culture of the system design. Then comes the safety of the intended function. This is mainly related to the nominal functionality of the function or of the it could be up to L5 functions, so L3, L4, and L5 function. How to make sure that the design that is created by the designer is safe enough, so the intended functionality is safe in itself. Then comes the cybersecurity part. So this, all the standards like 21434, it talks about the cybersecurity. So in our case, it's mainly touches more or less all these domains of standards. Okay, so now it's time to give an example, like what I meant, like when we want to simulate some use case in a simulation environment. So here in the autonomous drive system, in order to, so one more thing before I start explaining the scenario here. So this, whatever vehicle which is under test, that's we call ego vehicle, which in our case here is that red vehicle, and then there are vehicles which are the participants for the use case or a part of the use case within the simulation environment. So those are the participant vehicles. So in case of autonomous drive system, there is one feature of ADS which is autonomous drive system, is to keep the lane and make the maneuvering as safe as possible. So it kind of generates two paths at the same time. One is the normal path, which the vehicle tends to drive on, and the other is the backup path. And the backup path activates in case there is some emergency happens or some faults occurs that the vehicle cannot continue with the normal path. So it just activates the backup path and activates the fallback basically to safely and securely stops the vehicle at some point in the simulation. So what can we do here? So the maneuver is based on the sensors and the GPS input that the vehicle understands its environment, where it is in the road, for instance, what's the heading of the vehicle and speed of its own vehicle and the other vehicles. So that is it actually the ego vehicle use the sensors to get all that information or the GPS information. So if there is any error in the sensors or any error in the GPS happens, then there is a possibility that the vehicle will not be able to continue the normal path, or if there is a possibility that the vehicle some fallback strategy within this vehicle will activate. So the purpose of fault and attack injection is actually to analyze the behavior of the vehicle in terms of fault and attacks, and to make sure that the output in case of faults and attacks, the vehicle maneuvers safely, and also ensures the safety of the other participants of the scenario. Okay, so now it's our method that we are focusing on. It is simulation-based fault and attack injection on system level. I have talked about the simulation-based verification and validation, and I also talked about the importance of faults and attacks into the simulation. So the purpose, again, is to inject faults and attacks at system level to evaluate the system's dependability by injecting faults and attacks. Then the focus is basically on sumo-based fault and attack injection. So the focus is on the vehicle here, vehicle system, subsystem, or functions or sensors, and analyze the behavior of the vehicle or the surrounding vehicle as well under the influence of faults. Then comes the sumo vanes-based fault and attack injection. Here the focus is on the communication part of the vehicle. That could either be V2V, vehicle to vehicle, or V2X, vehicle to any infrastructure. And then analyze the behavior of the vehicle under the influence of faults and attacks. Then I would like to present the architecture of sumo-based fault and attack injection that we have looked into. So in sumo-based or sumo traffic simulator, there are car following models, lane change models, road features, car attributes, and scenarios. So we can have all these by default, and there are some added by which are results of some really good projects. So those models are added later into the sumo traffic simulator. There is TraceEye, which is basically short term for traffic control interface, and that gives the access to a running road traffic simulation. It allows to retrieve values of simulated objects and to manipulate their behavior online. So in this case, in our case, we have a fault injector that we use TraceEye to connect to the traffic simulator, and the purpose of the fault injector is to inject different types of fault models, and also to define the location where we want to inject the faults, what type of faults, how long that the fault should persist, and also at what time we inject the fault injection time. Finally, in the architecture, it's a database which is used to log all the available parameters of the sumo traffic simulator, or the specific parameters that we are interested in, and also some data or parameters that we would like to store or log from the fault injector. We have a paper already, so some of my colleagues, Mehdi, Maliki, and Berosh Sangcholi, they have already written a paper on this. So here is the source on the bottom: simulation-based fault injection in advanced driver assistance system modeled in Sumo, and that talked about this fault injector. Which is also called SUFI, simulation-based fault injector. So please go to, so this paper has been accepted already, and if I am correct, the GitHub page will also be provided so that researchers can go in and just try the tool and see what we have done and if more can be done. So please go and read this paper if you are interested and want to know more about it. Okay, so just continuing with the Sumo, so as I mentioned, so Sumo has some models available that we can use. Those models include the ACC and CACC as car following models, and provide some mode speed control, gap closing control, and collision avoidance features or modes. On top of that, it also provides the lane changing model and intersection models. There are some other models also available that I haven't mentioned here, but those are such as Kraus and IDM. Those are the default models within Sumo. Okay, so scenario, I've already talked about the usefulness or the importance of the scenario, and that's also is the same in the Sumo scenario. So we really need to think about what functionality we want to test and what type of scenario we want to have. Because when we talk about the scenario, there can be millions and millions of scenarios that we can create and that can actually verify and validate a very specific part of the function or a system. And we need to make sure that how much scenarios we need in order to fully verify and validate a system. If not fully, then at least to verify and validate to an extent which is acceptable by the end user and by the certification authorities. Okay, so I think now it's time to provide a demo. So this is the SUFI demo, simulation-based fault injector demo. So I will be showing you guys a golden run of the demo and then the faulty run of the demo. So here, the first one is the golden run here. So you see there is a very specific use case where we have vehicles in specific settings, which are moving together with the ego vehicle, which is the vehicle under test. And then the vehicle tries to accelerate if there is enough gap between the vehicle in front, or it will try to change the lane if there is enough gap between the vehicle on the adjacent lanes. So we see what happens. So I just play these video that we have recorded. Okay. So now the vehicle is moving in the middle lane, tries to go to the left lane. It has the indicators on, but you see the vehicle on the adjacent lane never allows that vehicle to change the lane because the minimum gap between the ego vehicle and the participant vehicle was not enough. So that's how the simulation ends. Now I will be showing you guys the faulty run. So the fault here is basically the fault in the gap and speed of the vehicle, which means in our case is that the vehicle overestimates the gap and speed with the vehicle in front. And see what happens. Okay. So now it's a faulty run. So the simulation or the target time of the injection is 11 seconds to 21 seconds. So at that point, we have injected the fault, and we see that the vehicle couldn't maintain the gap because it overestimates the speed and the gap between the vehicles. So it kind of accelerates until it activates the emergency braking, and then there is a distance. Little bit increase between the vehicle, then it accelerates again, and then goes into the same situation and tries to do the same thing until the end of the simulation. Okay. So as I said, like we have been, SUFI is basically is very much focused right now into the Sumo. So Sumo is the environment where we can do lots of things with the vehicle, microscopic simulations, but there are some limitations in Sumo as well. Like if we want to have a really high fidelity sensors or sensor models, that is not provided in Sumo. The vehicle to vehicle and vehicle to infrastructure communication possibilities are also non-existent in Sumo currently. Also, the advanced vehicular dynamic models, advanced steering and braking models, which have been verified and validated by the real vehicle steering and braking functions. And finally, there have been work ongoing, but we haven't focused a lot into this. But this is the area which can improve, and that is to integrate the machine learning-based autonomous drive stack, so that that can give an opportunity to actually integrate the AD stack into the Sumo and tries to verify the actual function, AD or ADAS function into the Sumo environment. So these are the some limitations that I want to mention. Okay, so now what we have done or what I have presented so far is everything on this level. That's the vehicle level, which is in Sumo. So if we want to extend the scope of our verification and validation, we can add another tool, Vanes, that I have mentioned in my first slide, and that actually supports the inter-vehicle communication. So we can model different types of communications in Vanes, and it is kind of connected with Sumo as well. So now I will talk about the upcoming or the next verification method, which is Sumo-based fault or Sumo Vanes-based fault and attack injection. So this is the architecture that is presented in the website of Vanes. Here is the source here. If you are interested, just please go there, and there are more information present there. But here, briefly speaking, it is basically based on OMNet. That's the Objective Modular Network testbed, and also an IDE. And that actually gives an opportunity or possibility to integrate Vanes. So Vanes is the vehicles and network simulation. So it's a vehicular network communication framework. And that is connected to the Sumo traffic simulator. So all the vehicle mobility that happens in Sumo environment, and all the communication possibilities, like the modeling of the network layer or the physical layer or MAC layer, that is possible in Vanes. So if we induce or introduce some faults and attacks in the communication part, which resides here, then the effects we can see. If we want to see the effects on the vehicle, then we can see the effect in Sumo. So there is this, like, it's communicating bidirectionally by using the trace-I interface. Okay. So this is under development. This is Sumo Vanes-based fault and attack injection architecture. So here the idea is more or less the same. So as I said, that we wish to develop a framework or a fault injector that can insert different types of faults into the communication part of the whole system, which resides in the Vanes part, and that is connected to the Sumo simulator as well for the vehicle mobility. And there is also a possibility to log anything from Sumo or Vanes, or even from the fault injector. So there should, this bidirectional, but there can be another line here. So this is approach that we are thinking to have, but this is still under development. But this is quite similar to Sufi in the appearance, at least. Okay, so then for the Sumo Vanes-based fault and attack injection, I think it's also a good idea to provide an example as a demo that we have created for the platooning scenario. So the platooning scenario, there is the basic concept of platooning is that we have a ego vehicle, or we also called a lead vehicle, that is basically controlling the parameters of the following vehicle in a different way. It could be sequential, or it could be broadcast, or any other sequence that can have, but in this case it's a broadcast, you can see. Then the leader vehicle defines different parameters like heading of the platoon, the speed of the platoon, the gap that needs to be maintained within the platoon, steering and braking, as all that, for instance. That is not braking, because braking is the gap, and then all the other following vehicles, they maintain the gap by accelerating or decelerating, and that is based on the sensors of each vehicle here. So it's a simple platooning scenario where we can inject communication faults and attacks. So some examples of faults and attacks are replay attack that we can use, jamming attacks, or data injection attacks, etc. So that's how it looks like in the simulations. This is again a Sumo GUI. So here you see there is a platooning scenario established where we have the platoon leader, the first vehicle always, and then we have, in this case, 4 following vehicles. So I think it's a good time to see a demo for the platooning scenario jamming attack. So let me just play the video. Here there is, you see, it's the nominal platooning scenario, and at time 11 there will be a fault, a jamming fault, where there is no communication between the leader vehicle and the following vehicles. So of course in the simulation we see it just crossed, but in here you see it's a collision. So the vehicles kind of stop getting the information, so it couldn't tell if there is a vehicle in front or not, so it just keep on going and crashed into the leader vehicle. So that was a simple demo we wanted to show you, just for your interest, like how it looks like when there is some type of attack into the platooning scenario. And one more thing that I would like to mention here, that that was a sinusoidal scenario where the vehicle was accelerating and decelerating. So the attack when we have injected that was when the leader vehicle was decelerating. Okay, I think I've shown this. Next slide. Okay, so now what we have covered. So we have covered the vehicle part of it, that is Sumo based. And we also extended the scope of the verification and validation for faults and attacks, or for safety and security, into the inter-vehicle communication domain as well. So we have integrated VANs to Sumo. As I said before, there are some limitations in Sumo, and that cannot be covered in VANs as well. And that is, if we want to have a really good high fidelity sensors, we can have them as well, and that we can have through Carla. So Carla provides better sensors. So we can look into what type of sensors Carla has and integrate those sensors into the system, and then try to inject faults into the sensor part of it and see how the vehicle behavior will be. Okay, so my last slide is to summarize. I hope I didn't take a lot of time here, but summarize here. Summarization is, I talk about the simulation, the importance of verification and validation in the simulation, that is increasing. It has increased a lot lately, and now it is considered as a necessary part of the VNV, not just a necessary part of the VNV, but most verification and validation will be done especially in the automotive industry, in simulation, which is representable with the original or testing in the real world. But those results will, of course, be comparable. I have also talked about the Sumo-based fault and attack injection, and Sumo VANs-based fault and attack injection. And I also mentioned a little bit of the future work that we can also extend this to where we have a real high fidelity sensor models in Carla that we can attach in the system and try to do some sensor fault and security-based testing on the sensors. Yep. So I think it's time for questions. Thank you so much for listening.
We now end the first part of VALU3S First Training Session. We sincerely hope that you have enjoyed it and that it was a fruitful set of presentations on important topics for verification and validation of automated systems. Thank you for watching.